Now, we'll explore PagedAttention, a new type of attention mechanism designed to make memory use in large language models much more efficient. It takes inspiration from how computer operating systems manage virtual memory, enabling LLM to handle memory more flexibly and avoid common issues during inference processes. Let's explore it in 6 parts. The PagedAttention architecture. How does PagedAttention improve GPU utilization? The copy-on-write mechanism in PagedAttention. How does the block table work in PagedAttention? What specific optimizations does vLLM offer alongside PagedAttention? How does vLLM's continuous batching work in conjunction with PagedAttention? Let's discuss the PagedAttention architecture. The first. Key concepts of PagedAttention. Let's break down a few key ideas. 1. KV cache management. In traditional LLM, as tokens are generated, the key value cache grows continuously. This can lead to wasted memory. PagedAttention solves this by dividing the KV cache into fixed-size blocks. These blocks can be stored in non-contiguous memory locations, helping to avoid problems like internal fragmentation, waste within a block, and external fragmentation, waste due to scattered memory allocations. By using uniform block sizes, memory management becomes much more efficient. 2. Logical and physical blocks. PagedAttention makes a distinction between logical blocks and physical blocks. Logical blocks represent the way data is organized for processing, while physical blocks are the actual memory locations where the data resides. There's a table, called a block table, that keeps track of where each logical block is physically stored. This allows the system to manage memory dynamically and efficiently as new tokens are generated. 3. Block table. This table is crucial because it tracks which logical blocks map to which physical blocks. It also monitors how much space within each block is occupied. This enables flexible memory management as the system processes new data, making sure memory is used optimally. The second. Operational mechanism. Let's look at how PagedAttention actually works. 1. Partitioning. The KV cache for each sequence is divided into smaller, fixed-size blocks. Each block stores the keys and values for a set number of tokens, making memory management more flexible. 2. Attention computation. Instead of processing the entire sequence of tokens at once, PagedAttention fetches these KV blocks individually. This reduces the memory load, as the system only focuses on the relevant data for each step, rather than holding everything in memory at once. 3. Memory sharing. PagedAttention also allows for more efficient use of memory across multiple sequences. By using a technique called copy-on-write, it allows different sequences to share the same memory blocks, only duplicating memory when something is actually modified. This saves resources during operations like parallel sampling and beam search. 4. Performance optimization. By reducing the overhead of managing memory, PagedAttention can significantly improve throughput, up to 2 to 4 times faster than older systems like Faster Transformer and Orca. This is especially useful when working with longer sequences and larger models, where memory efficiency becomes a critical factor. The third. Benefits of PagedAttention. Let's summarize the key advantages of PagedAttention. 1. Reduced memory footprint. The way PagedAttention manages the KV cache almost eliminates memory waste. This means we can process more sequences at once, which is crucial for scalability. 2. Increased throughput. Better memory management means better GPU utilization, which leads to faster processing times. This results in improved overall performance, especially for large-scale LLM applications. 3. Flexible memory allocation. By separating the logical organization of data from its physical storage, PagedAttention allows for dynamic adjustments as new tokens are generated or new requests are made. This flexibility makes it highly effective in handling different types of workloads. In summary, PagedAttention is a significant breakthrough in optimizing memory for large language models. By using techniques borrowed from operating systems, it improves memory usage, allowing for faster and more efficient processing, even for very large models and longer sequences. This makes it a key advancement in the performance of modern LLM, as demonstrated in systems like vLLM. Now let's look at how paged attention enhances GPU utilization, which is a key factor in making large language models faster and more efficient during inference. Paged attention improves GPU utilization through its innovative memory management techniques, helping to make the best use of available memory resources. Here are the main ways it does this. The first, dynamic memory allocation. 1. Non-contiguous memory blocks. Traditional methods allocate fixed blocks of memory for the key value cache, and those blocks need to be contiguous. However, paged attention takes a different approach. It splits the KV cache into smaller non-contiguous blocks, meaning memory is allocated in a much more flexible way. This reduces wasted space, which is often caused by fragmentation, both internal and external. 2. On-demand allocation. Another important aspect of paged attention is how it allocates memory dynamically, only when it's actually needed. This ensures that memory is used as efficiently as possible. It minimizes both internal fragmentation, wasted space within blocks, and external fragmentation, unused gaps between blocks. By allocating memory only when necessary, paged attention ensures that the GPU's memory is used to its fullest potential. The second, increased batch sizes. 1. Enhanced memory efficiency. Paged attention's efficient memory usage allows the system to process larger batch sizes during model inference. A larger batch size means that more requests can be processed simultaneously. This is important because the more requests we can handle at once, the better we can utilize the GPU and avoid periods where the GPU is idle. 2. Throughput improvement. Larger batches lead to better GPU performance, which directly translates into increased throughput. In fact, benchmark tests show that systems using paged attention can process 2 to 4 times more requests compared to traditional systems, especially when handling longer sequences and larger models. So not only does the system process more requests, but it does so faster. The third, efficient memory sharing. 1. Shared KV caches. Paged attention also allows for memory sharing across different requests. This means that when you generate multiple outputs from the same prompt, such as in parallel sampling, the system can use the same KV cache for all these outputs. This reduces the overall memory footprint because instead of creating duplicate caches for each output, the system can share the same memory blocks. 2. Copy-on-write mechanism. To ensure that this memory sharing doesn't cause problems, paged attention uses a copy-on-write mechanism. This mechanism tracks reference counts for the physical memory blocks, ensuring that data isn't corrupted. The memory is only duplicated when necessary, which helps keep memory usage low while allowing multiple processes to safely share memory. The fourth, handling memory constraints. 1. Swapping to CPU RAM. If GPU memory becomes full, paged attention can swap some of the KV cache to CPU RAM. This is like a swap space where memory can be temporarily stored on the CPU while the GPU continues to work on other tasks. This helps the system keep processing without running out of GPU memory, effectively expanding the GPU's capacity by leveraging additional resources like CPU RAM. 2. Reduced memory overhead. Paged attention also reduces memory usage associated with complex tasks, such as those required for algorithms like beam search. By cutting down on the memory overhead by as much as 55%, it makes the GPU more efficient during these intensive operations. In summary, paged attention improves GPU utilization by managing memory more efficiently. It reduces waste, allows for larger batch sizes, enables effective memory sharing, and even swaps memory to CPU RAM when necessary. All of these improvements result in higher throughput and better overall performance for LLM applications. This means faster processing and more efficient use of the GPU, especially when dealing with large models or long sequences. Now let's go over how the copy-on-write (COW) mechanism works in paged attention and why it's so important for managing memory in large language models. The first, shared memory management. 1. Initial sharing. When we have multiple sequences or requests generated from the same input prompt, Paged attention allows these sequences to share the same physical key value blocks in memory. Think of this like how different processes in an operating system might share memory pages. By doing this, paged attention avoids unnecessary duplication of data, which would otherwise waste memory. 2. Reference counting. To manage this shared memory, paged attention keeps track of how many sequences are using the same physical block of memory. This is done through reference counting. Every time a sequence maps to a shared block, the system increments the count. This way, the system knows exactly how many sequences are accessing the same block at any given time. The second. Modification. Handling. 1. Triggering copy on write. Here's where the real magic happens. When a sequence tries to modify a shared KV block, that's when the COW mechanism kicks in. The original block is marked as read-only to prevent any changes from being made to it by sequences that are still sharing it. 2. Page, fault, and duplication. If a sequence needs to write to this read-only block, a page fault occurs. This means the system detects the attempt to modify the block, and it creates a new physical block. The contents of the original block are then copied into the new block, and the sequence's mapping is updated to point to this new block. Now, the sequence can modify its own copy without affecting other sequences that are still using the original block. 3. Isolation of changes. This is a key feature. By creating a copy only when modification is needed, COW ensures that each sequence gets its own isolated version of the data. This isolation prevents changes made by one sequence from spilling over and impacting other sequences, which is crucial for maintaining data integrity in concurrent operations. The third. Efficiency gains. 1. Memory savings. The COW mechanism is highly efficient in terms of memory. Since it avoids duplicating data unless modifications are required, multiple sequences can share the same memory space as long as they aren't making changes. This minimizes the overall memory usage. 2. Performance improvement. This strategy leads to significant performance gains. For example, in scenarios like parallel sampling or beam search, where multiple outputs are generated from the same input, paged attention can cut memory usage by up to 55%. As a result, it achieves performance improvements of up to 2.2 times compared to traditional methods. In summary, the copy-on-write mechanism in paged attention allows sequences to share KV blocks until modifications are necessary. When a modification occurs, a copy of the block is created, ensuring that changes don't affect other sequences. This approach not only reduces memory usage, but also improves performance, especially in tasks like parallel sampling and beam search. It's an efficient way to handle memory, particularly when you need to manage multiple sequences in large-scale LLM inference tasks. Now let's take a closer look at the block table in paged attention and understand how it plays a key role in managing memory efficiently for large language models. The first. Mapping logical to physical blocks. 1. Logical blocks. In paged attention, the KV cache, which stores key value pairs, is split into logical blocks. These blocks each contain the key and value vectors for a specific number of tokens. For example, if the block size is set to 4 tokens, then each logical block will hold the keys and values for 4 consecutive tokens in the sequence. 2. Physical blocks. These logical blocks aren't stored in one big contiguous memory block. Instead, they are mapped to non-contiguous physical blocks in the GPU memory. This allows the system to use memory more flexibly. Essentially, this mapping works in a similar way to how virtual memory management works in operating systems, where memory doesn't need to be in one continuous chunk to be used efficiently. The second. Structure of the block table. 1. Entries. The block table is like a map that keeps track of where each logical block is stored in physical memory. It records each logical block's corresponding physical block and also keeps track of how many positions within that block are already filled. This helps the system know how much space is being used and whether there is room for more tokens in a block. 2. Dynamic updates. As new tokens are processed during inference, the block table is updated dynamically. For example, If a new token can fit into an already partially filled logical block, the table updates to reflect this change by increasing the count of filled positions. If the logical block is full, new tokens will trigger the allocation of additional physical blocks. The third, efficient memory management. 1. Reducing fragmentation. The key advantage of using a block table is that it helps minimize memory fragmentation. By allowing for non-contiguous memory allocation, the system can reuse memory space more effectively. Traditional memory allocation methods, which require contiguous memory, often leave gaps that can't be used efficiently. With this approach, memory is allocated and used in smaller, flexible chunks. 2. Optimized access. During the attention computation phase, PagedAttention uses the block table to quickly find the right KV blocks it needs. Instead of loading entire sequences into memory, it can directly access only the necessary blocks. This speeds up the process and ensures that memory isn't wasted by loading unnecessary data. In summary, the block table in PagedAttention is a critical tool for managing memory. It connects logical KV blocks to non-contiguous physical memory blocks. This mapping allows PagedAttention to efficiently allocate and update memory resources, reducing fragmentation and speeding up memory access. Ultimately, it makes memory usage more effective, especially when processing large-scale tasks in LLM serving systems. Now, let's go through some of the specific optimizations that vLLM brings to the table, especially in combination with PagedAttention. These optimizations work together to boost performance, reduce memory usage, and improve overall efficiency when working with large language models. The first, continuous batching. vLLM supports continuous batching of incoming requests, which means it can process multiple requests at the same time. This is key to making sure that the GPU resources are being used as efficiently as possible, avoiding idle times. By keeping the GPU busy, vLLM maximizes throughput, which helps in handling a higher volume of requests without significant slowdowns. The second, optimized memory management. 1. Dynamic memory allocation. Instead of reserving memory upfront for the maximum token lengths that might be needed for output, vLLM uses a paging scheme. This means memory is allocated dynamically based on the actual decoding lengths required by each request. This method reduces wasted memory, making better use of the available resources and preventing overallocation. 2. Near optimal memory usage. Thanks to the integration of PagedAttention, vLLM achieves near optimal memory usage. In fact, it uses less than 4% of the memory in the KV cache, whereas traditional systems often waste between 60% and 80% of memory. This efficiency is a game changer, allowing vLLM to handle larger batch sizes with fewer GPU, which ultimately improves performance and reduces resource requirements. The third, advanced CUDA kernel optimizations. One of the major advantages of vLLM is its use of custom CUDA kernels that are fine-tuned to enhance performance during attention computations. These optimized kernels are specifically designed to work seamlessly with PagedAttention, ensuring that every operation is as efficient as possible. This reduces computational overhead and improves speed. In summary, vLLM offers a range of optimizations, including continuous batching, dynamic memory allocation, and custom CUDA kernels. These optimizations work together with PagedAttention to significantly improve memory usage and throughput. The combination of these features makes vLLM a powerful and practical solution for deploying large language models with optimal performance and reduced resource consumption. Now let's break down how vLLM's continuous batching works together with the PagedAttention mechanism to optimize the inference process for large language models. This combination offers significant improvements in throughput, reduces latency, and enhances resource utilization. Here's how the two components work together. The first, dynamic memory allocation. 1. Just-in-time buffer allocation. With PagedAttention, memory for key value caches is allocated dynamically, as needed. Instead of allocating a large memory buffer up front, vLLM allocates memory on the fly, based on the actual requirements of the sequence being processed. This flexibility ensures that memory is only allocated when it's necessary, adapting to varying sequence sizes and avoiding waste. 2. Efficient use of non-contiguous memory. One of the benefits of PagedAttention is that it allows KV pairs to be stored in non-contiguous memory blocks. This approach allows memory to be allocated more flexibly, reducing both internal and external fragmentation. Because of this, vLLM achieves near-optimal memory usage, with less than 4% waste, allowing it to batch more sequences together and improving throughput. The second, continuous request handling. 1. Merging incoming requests. Continuous batching enables vLLM to handle incoming requests dynamically. Instead of waiting for a batch to be full before processing, vLLM immediately merges new requests into ongoing batches. This means that as soon as a request arrives, it can be processed right away, without having to wait. The result? Maximized GPU utilization and minimized idle time. 2. Higher throughput and lower latency. By continuously feeding the GPU with data, vLLM reduces the time spent waiting for a full batch to form. This speeds up the inference process, leading to faster response times for real-time applications. At the same time, multiple requests can be processed simultaneously, increasing the throughput of the system. The third, enhanced memory sharing. 1. Shared KV caches. When generating multiple outputs from the same prompt, such as during parallel sampling, PagedAttention allows different sequences to share the same KV cache. This sharing of memory resources helps to significantly reduce the overall memory usage. This means that vLLM can handle more requests simultaneously without needing additional memory allocations, thus improving efficiency. 2. Copy-on-write mechanism. If a sequence needs to modify a shared KV block, the copy-on-write mechanism ensures that changes don't affect other sequences using the same block. With copy-on-write, PagedAttention can handle modifications independently, which means sequences can still share memory resources without worrying about conflicts, maintaining performance even during continuous batching. In summary, vLLM's continuous batching works seamlessly with PagedAttention to enable dynamic memory allocation and efficient handling of incoming requests. By continuously merging requests and improving memory sharing, this combination results in improved throughput, reduced latency, and optimal resource utilization. This makes vLLM a powerful and efficient solution for serving large language models in real-time applications.